Welcome everyone to the Systems Engineering Ezra seminar series. Today we have Sharon D, who's an associate professor from Columbia, the Civil Engineering and Engineering Mechanics department. She's been doing a lot of work at the intersection of game theory and transportation, and is going to talk about that today. Welcome, Sharon. Thanks for the talk. I'm looking forward to hear what you have to say.
Yeah, thank you, Samisa, for the invitation and also the nice introduction. I really hope that I can go in person this time, but hopefully in the not far near future that I can meet everyone in person. And this is a joint work with my student postdocs and also collaborators from Applied Math. In this talk, I try to answer a research question that is kind of challenging in transportation nowadays. Is if we think about maybe 5 years to 10 years from now on, and there are already a significant portion of autonomous vehicles running on public roads, and they interact with human drivers. How do we control or optimize the fleet management of these autonomous vehicles? And what we really want to consider first is what's the optimal control problem we should formulate for the autonomous vehicles. When they are running on a road network, they first need to determine what's their speed choice when they move along a road link or segment. But at the intersection or junction point, they also need to determine which route they want to take, or what's their turning ratio. However, as I mentioned, if there are a lot more autonomous vehicles on the roads and they interact with each other, so then they not only one optimizes its own objective function while others are also doing so simultaneously, then this forms a game. So how do we solve this game? And derive some equilibrium-based and optimal control policies. The last question we are interested in answer is, how do we infer the human behavior when they interact with the autonomous vehicles? And in this talk, I will introduce how we leverage game theory, in particular Midfield Game and control, and also machine learning, in particular physics-informed deep learning to solve this problem. So before I delve into methodology, let me show you a video clip from basically driver recorded inside his car. So this is a Waymo car trying to merge to the highway main line. So you can see its left turning blinkers on. And all the other human drivers in the neighborhood of this car were able to successfully merge to the mainland. However, this car failed to do so and had to get off the highway from the next off-ramp. So from the human behavior perspective, this doesn't make any sense. I think there are many reasons this happened. And one reason probably nowadays, the autonomous vehicles are controlled using more towards control-based methods, or I call it a control agent. However, people realize that in both the academia and the industry that we really need to model them as AI agents. So what do I mean by artificial intelligence here? It's that we need to treat each autonomous vehicle as a rational agent or game player. Their goal is to optimize some utility function. And then they either play a cooperative or non-cooperative game. And they need to develop this capability of learning and adapting to the emerging traffic environment. In industry, people nowadays use machine learning, like deep learning, reinforcement learning, to model the control of an autonomous vehicle. And here, my approach is to basically model the interaction between the autonomous vehicles and human-driven vehicle as a game system. And I think that game theory is one way to empower the driving intelligence of these vehicles. And then if you go to YouTube, you can find many other related videos, like I showed one here. It's from also YouTube. Basically, somebody uploaded. So when this Waymo car, basically it's very hard for human to predict how they behave at the intersection. And this Waymo car actually stop when the green traffic light is about to switch to yellow. But for human driver, usually they just accelerate and cross the intersection. And another video is, basically,
which was driving down the street.
When there's no lane marker on a road, especially in residential area, so this Waymo car actually initially was driving in the center of the road. And then when it see a car on its left-hand side, it was confused and stopped, doesn't know what to do. So there are many this kind of videos showing how socially awkward the autonomous vehicle behave. So my research doesn't aim to solve this problem all at once, but hopefully we can open up the discussion on how we can introduce game theory to manage autonomous shared vehicle fleets in the future. And so let me describe the setup of the problem. So we start from so-called the N-car differential game. And I use the ring road as an example, but this game can be formulated in a more generic scenario. So assume on the ring road, there are multiple autonomous vehicles, or I call it AV from now on, driving counterclockwise. And then each car, let's look at just this green car, its location is denoted as xn and the velocity is vn. Their goal, basically, when we apply this differential game and then approximate to Midfield Game, so the methodology is scalable, which means we can use this equilibrium to control many vehicles simultaneously. Also, we found out the connection between this game theory and we call it a new type of traffic flow theory. So I will describe how we apply this method. We assume every car here has an objective function called J, and then this J is composed of two parts. The first Fn, big N, we call the cost function, it's time dependent. So it can include any terms describe the car's running cost, congestion, safety, or emission. So you can add whatever terms you want your car to consider while optimize its driving policy. And this V is it's the terminal cost. So basically, at the end of the driving horizon, denoted as big T. So what cost we want this car to achieve. And then our interest is a Nash equilibrium of the velocity control for car N. So the definition of this equilibrium is that when other cars fix their control strategies at V minus N, so this car, when it adopts this equilibrium control Vn star, so it will have a minimized objective. And so differential game, this is the setup, and it's, I think, basically you can treat it as a coupled list or system of optimal control. So each car is solving its own optimal control problem, everyone, but they interact with each other. So one's action may influence others. So this game becomes not scalable when the number of the cars grow in the system. So what we do is we introduce so-called Midfield Game. And so what is a Midfield Game? This concept was proposed by two groups of people back in 2006 and 2007 independently. And so this game aims to solve a decision-making process for multi-agent dynamic system. So basically in the dynamic system, every agent play so-called non-cooperative Nash game. However, because the number of agents is large, so this mean field approximation can be applied to basically go to so-called n-player limit. When we let the number of agents go to infinity, then the game moves from the differential game to mean field game. And since its inception, this game is demonstrated its robustness in explaining the social phenomena, including Mexican wave and also fish schooling. The reason is because it can bridge the microscopic agent level optimal control problem to macroscopic mass level dynamic system. So I will skip the detail about mean field game, but let me talk about how we apply this mean field approximation to the differential game we set up at the beginning. Still the ring road, and we have multiple AVs running. So when we let the number of agents goes to infinity, then this objective, we can remove all those n subscript. And then we have one generic cost function f. And if we look at that green car, which is the initial we denote as the car n, but now we can remove its index. So this become a generic car. So, and we assume every car is homogeneous. So their contribution to the system is marginal. And then once we have this approximation, this generic car doesn't see the discrete car in its neighborhood. Instead, it can only perceive the traffic density in its neighborhood. So we use this heat map to represent the traffic density, basically the spatial distribution of cars. And instead of solving a Nash equilibrium, now we are trying to solve so-called mean field equilibrium. So it consists of two dynamic fields. U is we call it the traffic velocity field, and rho is the traffic density field. How do we solve this mean field equilibrium? We use so-called forward-backward equations. Let's start from the agent dynamic. So each car in the traffic stream, they try to react to all the neighboring traffic environment and solve an individual optimal control problem. And once we apply this mean field equilibrium, so then this generic car solve a generic optimal control problem. So the V is the speed of this generic car, and J is the objective function. So when we solve this objective function, we assume rho, which is the traffic density, is known. Given rho, then we can solve this optimal control problem, and then we can feed back the U, which is the velocity field, back to the so-called mass dynamic. So mass dynamic describes how the traffic population moves. Here we use flow conservation equation. In this flow conservation equation, we assume U is known, and we try to solve the traffic density rho. And then this goes back and forth until it converges, then an equilibrium can be obtained. And we call this agent dynamic as a HJB equation solved backwards. And the mass dynamic is the FPK equation and solved forward. So if I write out what this HJB equation looks like, so it consists of two equations. V is the optimal cost. We need to solve it, and the rho is the traffic density. So F is a common mathematical transformation. I indicate what's it like here. And the FPK equation is just the flow conservation. So here I want to mention that the mean field game we focus on the deterministic system. Usually, I think when this game is applied to other fields, the FPK equation also have those viscosity term and also stochasticity term. The reason we assume it's constant, which means the right-hand side is 0, because traffic cannot appear or disappear all of a sudden. So we assume flow is exactly conserved. And how do we solve this system? There are three categories of methods. The first is variational form, but to use this, we need to assume this game is a potential game. So the cost function we focus on can be decomposed. Basically, the traffic density rho and the traffic velocity u can be separate. But in our case, it's not separable. And I will explain why it's not separable in the next slide. And then fixed point iteration, it's quite straightforward. If we can solve the forward and backward equation iteratively, so eventually it can converge. But we found out that in our case, when t is very large, basically the planning horizon is long enough, so this method also failed to converge. So we adopt the third method, it's the finite different Newton's method. Basically, we put the forward and backward equation into one big system and discretize it in time and space and solve the big equation. And then we apply Newton methods. Oh, sorry, I forgot to say, feel free to ask any question or leave question in the chat box along the way. Don't be shy or hesitant to jump in during my talk. Okay, so let me just talk about some finding we have found after we solved the Midfield game on the ring road. And so let me show that in this figure, the left side, we show how when we control this car using Midfield game, so how the system evolves. And the right-hand side is when we use LWR model. What is LWR? LWR is a first order traffic flow model. So it consists of two equations. The first equation is the flow conservation or transport equation. And the second equation defines the mapping between traffic density rho and the velocity u. And usually we call this fundamental diagram. So the second equation here is so-called fundamental diagram. It defines how given a rho, what is its value u. Okay, this is LWR, and then it's a scalar PDE equation. And for Midfield game, so we assume a cost function. This is the cost function we demonstrated before. It can contain different cost terms we want to optimize. And now I want to translate LWR, which is a PDE system, to a Midfield game setup. How do we do that? We can introduce a cost function that, given this cost function, the equation, the equilibrium of this game is equivalent to the solution of that PDE system. So this is the cost function we introduce. And U, big U of rho is so-called equilibrium speed. And UM is the maximum speed or speed limit. And so this utility function tells us that given under this LWR control, we want to basically obtain a speed that is exactly equal to the equilibrium speed. And then based on this, we try to develop a new cost function for Midfield game. So we keep the first term as the same. So basically this speed had to be close to the equilibrium speed as close as possible. But we add another term. So this rho J is the jam density. So basically when the highway is full of cars, so no car can move, what's the value? What's the maximum cars it can accommodate? And when we minus this term, it represents that this control how to try to avoid the crowd. So try to deviate its traffic density from the jam density. That's the meaning of the objective function we designed for the Midfield game. And then I will show you this animation and see how this under different controls, how the traffic dynamics evolves in different direction. We basically start from exactly the same initial condition, which means every car is positioned in the same location. And the top one shows the discrete position. And the bottom one is the basically the blue curve is the traffic density and the red curve is the traffic velocity. X-axis is the space. Basically, we unfold this ring road, and then we denote its length from 0 to 1. And you can see the initial density, which is the road curve. Here, so they have exactly the same shape for those two scenarios. It's bell shape, and we deliberately create this peak, which correspond to this area, which means there are some cars that are quite dense in this area. And I will show you how the traffic velocity and density evolves as time goes on. So you can see under the Midfield Game control, both the traffic density and velocity gradually converge to so-called uniform flow, which means they have the same speed and the same headway or gap distance while driving along the ring road. However, for the right-hand side, you will see this jump on both the speed and the velocity curve. We call it shock wave. So this corresponds to, on the ring road, this area. So basically, when the car have to approach this area, when there's high density, it have to slow down. So it shows that under Midfield Game control, if we can carefully design objective function, so it can smooth traffic flow very quickly. But if we use traditional car for traffic flow model to control autonomous vehicle, so it can cause traffic congestion and stop and go waves.
Sharon, can I ask a quick question? So I guess there are people who you try to do this with LWR as well, right? In that case, are they sort of looking ahead? And so what is the advantage of Midfield games? Are you able to do it somehow with less information? Or? Yeah,
so I think this is a very good point. So basically, what Midfield Game does is the cars can anticipate the traffic condition. If you remember, when we saw this Midfield Game, we have this both the forward and the backward equation. So when they solve this transport equation or flow conservation equation, they have to anticipate the traffic density ahead of the time. And then based on that, they will come back and solve their optimal control accordingly. However, for LWR, it has this equation, but the agent dynamic, it's more just the fundamental diagram. It's the mapping, direct mapping from row to U. It's a local mapping. So that's why for LWR, we can say that it doesn't have this anticipation behavior. But in terms of information, actually, for Midfield Game, it also mainly focuses on anticipate how the local road evolves. It doesn't care about the road in other places. So yeah, we call it global in time, but local in space. This is the characteristic of Midfield Game. But for LWR, it's local in time and local in space.
Right, that's super helpful. And then the way to get around that in LWR would be to look ahead, right? And that's the trick that people use. So here you don't need to do that. Look ahead in space is what they do, right? And you don't need to do that.
No, we don't do that. Yeah. So if we can do also modification on the top, it's called non-local model. Basically, they look ahead also in terms of the space. Yeah. So yeah, to accommodate that non-local model, basically we have to modify this flow conservation.
Thanks.
Yeah. Thank you for the question. So because it's, I try to introduce some traffic background. If you also have questions about what's the term means in the traffic background, so feel free to jump in. I can elaborate more. Okay, so now we demonstrate how the Midfield game works on a ring road. And now we want to look at a transportation network. So here, this is a subnetwork you can consider that is extracted from a large network. And assume this car moves from the node K to node I. So while driving along this road segment, its speed is controlled by the Midfield game we introduced in the previous part. So we solve the Midfield game, and we get this equilibrium, which is a velocity field U and density field rho. So that can propel the car to move from K to I. However, the next question is, how does this car make a route choice at the intermediate node I? So now we introduce some additional decision variables. Assume at node I that this car can only select either go into IR link or IJ link. And we introduce so-called beta, is the decision this car made at node I, given its destination is D. And if it's associated to the link IJ, we call the mixed strategy, which means its value can be only become between 0 and 1 is a probability. And if this is greater than 0, which means this car will be likely select the link IJ. Then based on this condition, we can formulate optimality condition, which means the left-hand side is the optimal cost from the node I to D should be equal to sum of these two terms. I will demonstrate what these two terms means just in a few seconds. And if this beta decision variable is 0, which means the left is smaller than the right-hand side, or we know that IJ is not an optimal path along this optimal link along optimal path from node I to D. So yeah, what is pi ID? Pi ID is the optimal cost, or we call the node potential from node I to the destination D. Similarly as pi JD is the optimal path from J to D. And the tau here is the travel time, or the travel time, the time lag from when the car moves from I to J. And this CIJ is basically the optimal cost. It's the cost that traversed by this car if it selects the IJ as its next go-to link. It's an integral of a cost function, and I think this showed up in the previous slide. It can be any terms you want to add in for the car to optimize. This is how we model the route choice at the nodes. Basically, we formulate the optimality condition, and then to formulate the mathematical formula, you can use variational inequality or a nonlinear complementarity problem. I will skip the detail here, but I want to point out one issue is if there's a queue at the node I, which means when the green car reached the node I, but there's already a car in front of it, then this car have to wait. Then we have to introduce another notation which is the queue. Queue we call the queue size. So here I assume the queue is modeled as a point queue, it's not a vertical queue, which means it doesn't occupy any spatial space. And then if there's a queue, then we have to solve a basic differential equation that the rate of the queue dissipation is equal to the inflow minus the capacity of that queue. And for point queue, we can assume capacity as a constant value. Once we introduce this queue, then we have to also calculate queue delay when we indicate this pi JD, which is the optimal cost from J to D, and assume it's a linear relationship, Q divided by the capacity. And also for the cost, when this car traversing link IJ, so we have to add also Q cost. And this cost is a monotonic relationship or function of the Q size. You can use linear function or nonlinear function. So I will skip how this big system looks like. Basically, we introduce the new equation. Here, one is the raw choice, variational inequality or complementarity, and also the Q equation, differential equation. I just would like to present how what's this under this big framework, how this mean field game works in a small network. So we use this as the demonstration network, and we assume the origin node is 1 and 2, and the flow from originating from 1 to 2 will end at node 4. 4 is the destination node. And the cost function we will specify is similar. It's the here we will consider running cost and the Q cost. The running cost has 3 terms. The first we call the kinetic energy. So U is the traffic density. U square is usually represent this the energy or the kinetic energy the car consumes. And rho divided by rho J, jam density, is the safety consideration. And this constant in the cost term, because it's integral over time, so this constant actually represents what's the weight of the traffic speed or travel time plays a role in this cost function. And the Q cost we define is basically a linear function with respect to Q delay. I also want to demonstrate under the LWR and the mean field game control, so how this traffic dynamics looks, how different it looks like. And I will use 2 figures. So left-hand side figure is the z-axis is the traffic density rho. The right-hand side figure is the traffic velocity. And the x-axis is the time, and then the y-axis is basically demonstrate how the flow moves along this path 1, 3, 4. Okay. This is how under LWR control, how this flow evolves in this small network. And this is how mean field game works. So I'd like to draw your attention to this peak. So in the traffic density, this peak represents when there's a high density in this area. Actually, this is when at around node 3, when the traffic stream coming from node 2 meets the traffic stream coming from node 1. And there's a bump because they almost reach at node 3 at the same time. So that's why it leads to a dip in the traffic velocity. But in contrast, you will see if we control it using mean field game, so this doesn't exist. So the flow, traffic flow is quite smoothed out. The reason is, again, like what Samisa asked. So because the traffic stream coming from node 2 can somehow anticipate how traffic density evolves. And then they found out, okay, there could be some potential conflict in the near time future. So in the near future. So that's why they decide to slow down a little bit and let the traffic from node 1 to cross the node 3 first. And eventually the whole traffic flow is smooth out.
Sharon, just another quick follow-up on this. So why couldn't the LWR also do this if it knew the boundary conditions and was trying to just do some, finite rise and optimal control? It will see it knows the dynamics, right? So we can let's say you discretize this as a CTM and did some finite horizon optimal control, why wouldn't the LWR approach also be able to anticipate what's going to happen and throttle accordingly?
So for LWR, the boundary condition we only provide is the only here, right, at the node 4. Basically, they need.
No, I meant if you knew the demand. Let's say 4 is an infinite sink, and then you knew what was coming from 1 and 2. Mm-hmm. You know the dynamics, right? The LWR will tell you how many vehicles are going to be at 3 at a certain time. So I'm not sure what kind of LWR optimization you're doing, but you could consider a LWR optimizer that is using the LWR again as the dynamics equations.
Yeah, so the reason is because for LWR, the speed, you don't directly control speed, right? So once you know the density along this link, speed is fixed. So there's no actual optimal control of the speed. So
okay, but I guess that's sort of a. I mean, you could still do variable speed limit based on LWR, right? So, or you could throttle it through ramp metering or something like that. So I guess it's a question of what your control is, but that's I guess not a fault of the LWR, but not using the appropriate control for that model.
We didn't add any control actually for LWR. So we just propagate the row, and based on row, we calculate the row yield for each link. So that's why it happened. Yeah, but you are right. If we can introduce another control for yield, imposed to yield, so it may also mitigate the traffic that way. Yeah, but LWR. So here, basically, I assume it's not a control model. So once you know the row, the yield is determined.
I see. So okay, so in some sense, the LWR is not doing control, but the Midfield Game is implicitly doing some control here because it's the agents are changing the behavior based on what's happening.
Yeah, exactly.
Okay.
Yeah, and I think you mentioned if we can impose an optimal control to LWR, so then it's along the line of this game theory. Basically, you also introduce some objective function, and then basically the system or the city planner has to determine the optimal yield based on that control. But here, the objective function, we impose it to individual car, and then let them play the non-cooperative.
I think that's maybe the key thing is that, yeah, you can do it with LWR, but you can do it in maybe a nicer way with this approach.
Yeah.
But you can also do it with LWR if you did the optimal control, I guess.
Yeah.
Okay, thanks.
Okay. Yeah, another thing is usually no matter LWR or other traffic model, so they on a network, we call the dynamic traffic assignment or DTA model. They always use the travel time as the objective function. But here, because we can introduce this FU, so this term, I call it efficiency, actually this controls how important this travel time is for the car to reach destination. But we can also introduce some other terms. So that's why for this system, the cars are not necessarily trying to reach to destination for as fast as possible, but also they try to balance out or trade off these kinetic energy and the safety factors. Okay, so any other questions? Let me move on to the next part. So here we introduce how this Midfield Game can be leveraged to manage a large fleet of autonomous vehicles on road networks. And in my research, we also apply control concept to basically design this game, Midfield Game, so that the traffic flow can achieve the certain goal we want to achieve. But because the time is limited, I will skip this part. But I will directly move to how we use the machine learning approach to infer the human behavior. And first, let me introduce how we model this mixed traffic coupled with autonomous vehicle and human drivers. So autonomous vehicle, we assume they are driven under this Midfield Game. And human driver here, we assume they follow so-called ARZ model. I will introduce what ARZ model is. And then for each system, they consist of two equations, flow equations. Each type of car, they have to satisfy this flow conservation for their specific vehicle class type. And then the traffic density of AV and HV, the sum is the total traffic density. And for Midfield Game, they have this HJB equation we described before. And then for the ARZ model, this is a momentum equation. We call this ARZ also second order traffic flow model because this term actually can be treated as the acceleration. So we not only control the traffic density and speed, but also acceleration. And this side is, U is with fundamental diagram. Basically, under ARZ, they try to control their speed to be as close as possible to the equilibrium speed when they consider how to control their acceleration. So the reason we use ARZ model instead of LWR model I described before in the first part is because ARZ model itself can generate a stop and go behavior. So it can be non-stable. So that's why we want to focus on the second order model to describe human behavior. So because we use ARZ to approximate human driver behavior, so it's essentially also a PDE system. You can calibrate this system using traditional methods. But here I want to introduce how we use the physics-informed deep learning to calibrate this, the human driving data. So now first, let me give you some brief introduction about how this machine learning model may fail and why we need a physics-informed method. So there's these two parts. One is the machine learning approach, one is the domain knowledge that have been developed in the past decades in transportation. Machine learning can have this advantage of discovering the mechanism directly from the data. However, it requires a huge amount of training data to discover the pattern. On the other hand, the domain knowledge or physics-based model can provide some physical consistency to regulate the machine learning training process. If we use this diagram to demonstrate the relationship between these two fields, we can see that x-axis is the amount of the data needed to train the model from low to high. And the y-axis is the amount of scientific theory needed. So physics-based model requires a lot of scientific hypotheses, but very small data to calibrate that physics. And on the other hand, machine learning model relies on a large amount of data and with very minimum information or prior assumption of scientific knowledge. And so recently, this physics-informed machine learning, or I will call it PIML from now on, has been booming because it can leverage the benefit of each domain. And for this part of work, our contributions, we apply this physics inform this framework to traffic state estimation using the real world human driving data. And we also develop this so-called machine learning surrogate model to estimate some traffic behavior that is inherent in the data. So let me first formulate how this problem is laid out. The physics-informed deep learning actually was initially proposed to solve PDE equations. So assume this is the well, basically the equation we are interested in solving. So rho Tx represents some physical value. It can be traffic density field or velocity field. And n of x is a nonlinear differential operator. And t is the time from 0 to big T, and x is the space domain. And our goal is to train a neural network that can approximate the solution rho Tx for this PDE equation. So assume this is the neural network parameterized by theta. And if we input one Tx pair, we will end up with one value of rho. And if this neural network is equivalent to the PDE solution, which means we introduce so-called residual. This residual should be equal to 0, basically the right-hand side of the PDE function. So now the problem is boiled down to how we can train a neural network that will lead to a residual being equal to 0. So let me show you the training process of this framework. Assume this is the neural network we try to train. We call it the physics uninformed neural network. And we have observation data or labeled data. So we can observe at some time point T and some location X. We know its measured traffic density. And we can also input this Tx and generate a rho from the neural network. So that we can compare the observed traffic density from the generated value coming from the neural network and calculate their discrepancy. Other than the observation data, we have co-location data. We call it unlabeled data. So we just randomly select some Tx pairs. We don't know the actual measured rho value at this Tx pair. But the neural network can generate a value. This value will be fed into a traffic flow model, and the lambda represents the parameter of that physics-based model. And then we can calculate residual defined in the previous slide. And this residual had to be close to 0 as possible, which means if this process is generated from the PDE solution, then the rho should be as close to the value computed from this traffic flow model as close as possible. Then we can define a loss function using the weighted sum of these two terms, and try to minimize this loss function. If it's not minimized, then we will go back to update the parameters in the neural network. Also, we need to jointly estimate the parameters that appear in the traffic flow model. So this is the whole process of training a physics-informed machine learning. And the upper branch represents the data-driven approach, and lower branch is the physics-informed path, because the physics will regularize how this residual value becomes eventually. And here we customize it a little bit. We introduce so-called fundamental diagram learner. What we changed is here. So instead of we have to jointly estimate the parameter in the original physics model lambda, here we replace it by another small neural network. We call it fundamental diagram learner. Then this becomes a machine learning surrogate model. And to train this, when we update lambda, this lambda is not the coefficient in the original physics model anymore. It's the hybrid parameter of that FDL neural network. And after we update this, then we can also get another physics uninformed neural network that can be used to generate the data on the test set. Okay, so now I will basically present the results using this approach for a real-world data, ngSim. ngSim is a widely used traffic data set. So basically, it's collected from a overhead camera that captured vehicles' trajectories for 15 minutes along highway in California. And the right-hand side is the heat map, or its exact solution, we assume, that we extract from these vehicle trajectories. So these are, we use this as the ground truth. And we assume to place the different number of sensors, fixed location sensor or loop detectors along this highway, which means we can only obtain the measurements where these sensors are located. Let me present the estimation error across several models we used. So the models we compared include 4 models. So the first 2 use the same physics, which is the first order traffic flow model, LWR. The last 2 is the second order ARZ model as the physics. And also for the within each group, we also either use the fundamental diagram learner or use a pre-calibrated fundamental diagram. And before I introduce the right-hand side figure, let's look at the left-hand side, how this model prediction error changes when we increase the number of sensors. We can see as long as we place more and more sensors, the estimation error decreases. So that is quite obvious. But I want to highlight that, so the orange line and the blue line represents the models that we use the fundamental diagram learner. So we don't directly estimate, calibrate the parameter in the physics. Instead, we introduce a neural network to learn that fundamental diagram mapping, which is the mapping from the traffic density to velocity. And on the right-hand side, we assume there are given only 3 loop detectors. So what's the fundamental diagram shape we estimate from that neural network? So the blue one is the LWR model with the learner. And then the orange one is the ARZ model with the fundamental diagram learner. So among these 4 models, I want you to focus on this area when the capacity is the highest. So this is we call it the critical traffic density area. And another is when the traffic volume is 0, which means the traffic density is the maximum. So you can see it's also the blue and orange lines achieve the best, which is the model when we introduce either LWR or ARZ as physics, but we also use fundamental diagram learning. So any question about this slide? So here, actually, I want to highlight one thing. So you may wonder, so this blue line is the LWR model. So the first order traffic flow model. The orange line is the second order ARZ model. So it's initially, we also didn't understand why when the sensor number is low, on the low side, we call the small data regime. So the first order traffic model actually performed better, outperformed the ARZ model. Because based on the transportation literature, people already found out the ARZ model, the second order traffic flow model can better capture humans' heterogeneity in human driving behavior. So the reason is because when there's a very small amount of data, so when we use second order traffic flow model as the physics, it's much harder to train that neural network compared to using the first order. So that's why we lack enough training data to regularize that training of the neural network. And that's why LWR performs better. But we believe that if we probably improve our algorithm, training algorithm, then this ARZ informed deep learning model should perform better than the LWR model. Okay, that's all about my presentation today. Thank you, everyone. And just quickly, talk about some future research direction. So I introduced how we use the game theory, control, and machine learning to solve the problem for the emerging transportation technology. And in the future, I really want to close the loop between these different methods. For example, ongoing work we are working on right now is to see how the game theory and the machine learning can be combined. Basically, the Midfield Game, when we solve the equilibrium, we still assume every agent can knows the environment, can predict how the environment dynamics evolves. However, if they lack that knowledge or they only have partial knowledge of the environment, then we need to assume these agents have to also first learn what this environment like, including they have to learn what's the reward they may get given they execute one action. So learning in game or machine learning based game, I think is also an active area. And we are working on the macro game. So how we can use reinforcement learning to solve an equilibrium in the game. Another loop we try to close is basically between the control and the game theory. So how we can introduce high-level control that will guide the equilibrium of the game towards the social optimal and can achieve the goal of the system performance instead of satisfying the individual interests. Thank you. Any questions?
Thanks, Sharon. Really interesting stuff. So I don't know if anyone on the Zoom has questions, they can ask directly. If anyone in the room has questions, maybe Daniel can help. Maybe they can just speak up and we can hear it. I guess in the meantime, maybe I'll ask another high-level question. So again, like, compared to using sort of other more standard like LWR type models with optimal control, are you comparing? Because right now in all of your comparisons, you're not comparing these methods against people doing control within the LWR system, right?
Oh no, yeah.
So I guess maybe how would they compare, and how would, I guess in the other extreme, how would this compare to machine methods that are completely like reinforcement learning driven, like maybe Kathy Wu, what she's doing. So I guess that's the full, like the best people doing purely control on LWR type models, the people who are doing completely data driven things, and now you have this sort of Midfield Games type approach. Like, what are the pros and cons for these methods? Is that something you've thought about? Is it something maybe that's future work?
Yeah, I think that's a good point. So yeah, because I think this field, especially for mixed traffic, now it attracts more and more researchers in the past few years. So it's kind of become a saturated field. And so yeah, different people use different angles to model this. This game approach, I think, basically we assume each agent is a rational game player, and then they have their own objective function they try to achieve. So here we assume they play a non-cooperative game. But for the most control methods introduced in this field, they assume it's centralized control. And they may develop some distributed control method. But basically, there's a traffic planner or city planner, or it's the AV manufacturer. They have a common goal, and then they assume these cars, they are coordinated and will follow whatever the control policy that the high-level planner try to impose. So I think this is the major difference here. And you mentioned the Casey Wu's work. So basically, theirs is they use the reinforcement learning, and they assume also it's coordinated. So every car coordinate with each other, and they optimize a common objective function. And so our argument is why we think it's a non-cooperative game, because if we look from a network perspective, let me just quickly switch to this slide. So when this car try to move in a network from point A to B, their goal is to deliver the passenger, the occupants, to the destination as fast as possible. So if they don't care about the social optimal, because if they follow social optimal, then some cars travel time are sacrificed. So that's why I feel as an individual agent, they don't have the motivation to coordinate or follow some central planner's view, unless you impose some external like effect, for example, like congestion pricing, toll, or some other maybe charge or cost that they impose to the environment. Then basically they still follow a non-cooperative mechanism, but the equilibrium can be guided towards that social optimum. So that's our argument.
Great, thanks. That makes sense. Yeah. See whether there is. I of course have more questions, but let's see whether anyone else has questions, and we can also talk offline. We're also at 1:25 now, so just see.
Yeah, so feel free to ask. I don't know whether probably it's too transportation oriented. If I didn't explain some concept clearly, also feel free to jump in.
Okay. Well, if there are no questions, then we can sort of conclude the talk. Thanks again, Sharon, for sharing this research with us. It's really interesting, and I'll just hang on the call and follow up with you on a few things.
Yeah. Thank you, Samisa. Thank you, everyone, for your attendance.